Today we'll talk about two applications of good feedback cycles: direct manipulation and invisible interfaces. Direct manipulation is the principle that the user should feel as much as possible like they're directly controlling the object of their task. So for example, if you're trying to enlarge an image on your phone, it might be better to be able to drag it with your fingers rather than tapping a button that says zoom in. That way you're really interacting directly with the photo. New technologies like touchscreens are making it more and more possible to feel like we're directly manipulating something even when there's an interface in the way. At their best, the interface actually disappears, which is what we mean by an invisible interface. With an invisible interface, the user has to spend no time thinking about the interface that they're using. All their time is dedicated to thinking about the task that they're performing. Our goal is to narrow the gulf of execution and the gulf of evaluation as much as possible. And arguably the ultimate form of this is something called direct manipulation. Now, today direct manipulation is a very common interaction style, but in the history of HCI, it was a revolutionary new approach. Now, to understand direct manipulation, let's talk about the desktop metaphor. The files and folders on your computer are meant to mimic physical files and folders on a desktop. So here on my physical desktop, I have some files. What do I do if I want to move them? Well, I pick them up and I move them. What do I do if I want to put them in a folder? I pick them up and I put them in the folder. I'm physically moving the files from where they are to where I want them to be. If files and folders on a computer are meant to mimic files and folders on a physical desk, then shouldn't the act of moving them also mimic the real-world action of moving them? Wouldn't it narrow the gulf of execution to leverage that real-world experience and that real-world expectation? Files and folders on my computer are meant to mimic files and folders on my physical desk. So we ideally want the action of moving them around on my computer to mimic the action of moving them around on my physical desk. But it wasn't always like this. Before graphical user interfaces were common, we moved files around using command line interfaces like this. The folder structure is still the same on the operating system, but instead of visualizing it as folders and icons, I'm interacting with a text-based command line. To view the files, I might need to type a command like ls, which I just have to remember. If I don't remember that command, I don't have much recourse to go find out what I'm supposed to be doing. To move a file, I need to type something like this. I have to type the command, the file I want to move, and the folder I want to move it to. Again, if I forget the name of that command or the order of the parameters to provide, there's not a whole lot I can do to recover from that. I need to run off to Google and find out what the correct order of the commands was, which is actually what I did before filming this video because I don't actually use the terminal very often. Then when I execute that command, there's not a lot of feedback to let me know if it actually executed correctly. I might need to change folders to find out. There I see the file is present in that folder, but I had to go and look manually. There's nothing really natural about this. Now don't get me wrong, once you know how to interact with this interface, it's very efficient to use. But when you're a novice at it, when you've never used it before, this is completely unlike the task of managing physical files on your real desk. Then the computer mouse came along, and with it came the ability to move a mouse around the screen. Equipped with this, my action of moving files and folders becomes much more direct. I can actually just click the file I want to move and drag it into the new folder. I get instant feedback by the fact that the file disappeared as soon as I dragged it over, and there was a sound effect that you may or may not have been able to hear. So now instead of typing in some cryptic command that I just have to be able to remember, I can just click on the file I want to move and physically drag it to the folder in which I want to have it. That's a very natural interaction. It mimics what I do on my physical desk. Moving the mouse around is a lot better than having to type in those commands, but the gulf of execution and evaluation are still present, especially for some novice users. There's still some interpretation that has to happen to understand that when I move my hand to the left on the mouse, the cursor on screen will move to the left as well. And while clicking feels kind of like grabbing, there's still some interpretation there. It's more direct than the command line, but there's still a gap. But modern touchscreens make direct manipulation more direct than ever. Let's say I want to put an icon into a folder on my screen. How do I do it? I hold down the icon and I drag it to the screen. The fact that if I wanted to move something around my desk, I would have to hold it down means that this is almost entirely direct manipulation. I don't need any prior knowledge to attempt to do what feels natural from moving that icon into that folder. That gives us a nice general heuristic to keep in mind. How do we help the user interact most closely with the target of their task? How do we make it so they're manipulating it as directly as possible? The seminal paper on direct manipulation interfaces came out in 1985, co-authored by Edwin Hutchins, James Holland, and Don Norman. We'll talk a lot more about Hutchins and Norman later in our conversations. Hutchins co-authored the foundational paper on distributed cognition, and Norman created one of the most accepted sets of design principles in his seminal book, Design of Everyday Things. But in 1985, direct manipulation was starting to become a more common design strategy. Hutchins, Holland, and Norman identified two aspects of directness. The first was distance. Distance is the distance between the user's goals and the system itself. This is the idea of goals of execution and evaluation that we talk about in the context of feedback cycles. They write that the feeling of directness is inversely proportional to the amount of cognitive effort it takes to manipulate and evaluate the system. In other words, the greater the cognitive load required to use the system, the less direct the interaction with the system actually feels. The authors break distance into two components, semantic distance and articulatory distance. Semantic distance refers to the difference between the user's goals and their expression in the system. In other words, it's how hard it is to know what to do. Articulatory distance is the distance between that expression and its execution. In other words, it's how hard it is to actually do what you know to do. You might notice that semantic distance encompasses our identify intentions and identify actions parts of our gulf of execution, and articulatory distance comprises that execute actions phase. This is brought together here in Figure 6 from this paper. Yeah, there we go. The user starts with some goals and translates those goals into the intentions in the context of the interface. They then translate those intentions into the form of the input, the actions, and execute those actions. The system then does something and gives back some form of output. The user then interprets the form of that output to discern the meaning of that output, and then evaluates whether or not that meaning matches their goals. So to take an example, when I brought up this figure, I needed to rotate the paper to display it correctly. That was my goal. I translated that goal into the context of the application, a rotate option that was probably hidden somewhere. I then identified the action, which was pressing the rotate button, and I executed that action. The system then did something and returned the output to me. The output specifically was the paper turned upside down instead of turned the way I wanted it. That was the form of the output. I then interpreted that form to discern the meaning that it had rotated it the wrong way. I evaluated that my goals weren't accomplished, and now I knew what to do next. I then pressed the button 2 more times to rotate it twice again, and the system then returned that output to me. I interpreted the form of that output to mean that the figure was now right side up, and I evaluated that that matched my initial goals. You might be able to see that this cycle is happening constantly whenever you're interacting with a computational interface. You could think of it in terms of broad tasks like searching a document for some keyword, or you could think of it in terms of each individual little tasks like interacting with the menus and pulling up the right prompts. But distance is only one component of direct manipulation. It's possible to have interfaces with very little distance that nonetheless are not examples of this kind of direct interaction. Everything we've talked about so far is true of feedback cycles in general, not just of direct manipulation. That's why the second component of this is direct engagement. What sets direct manipulation apart is this second component. The authors of the paper write that the systems that best exemplify direct manipulation all give the qualitative feeling that one is directly engaged with control of the objects, not with the programs, not with the computer, but with the semantic objects of our goals and intentions. If we're moving files, we should be physically moving the representation of the files. If we're playing a game, we should be directly controlling our characters. If we're navigating channels, we should be specifically selecting clear representations of the channels that we want. That's what takes a general good feedback cycle and makes it an instance of direct manipulation. We can shorten the goals of execution and evaluation in a number of ways without direct manipulation, but direct manipulation is a powerful method for shortening that distance. Virtual reality right now is making some incredible strides in facilitating direct manipulation in places where it just hasn't been possible before. Traditionally, when designers are designing stuff in 3D, they're forced to use a 2D interface. That translation from 2D to 3D really gets in the way of directly manipulating whatever is being designed. Through virtual reality, though, designers are able to view what they're designing in 3D as if it's in the room there with them. They can rotate it around with the same hand motions you'd use to rotate a physical object. They can physically move around the object to get different angles on it. So virtual reality is allowing us to bring the principle of direct manipulation to tasks it hasn't been able to touch before. But there's still a lot of work to do. Gesture interfaces like those used in virtual reality struggle with some feedback issues. We aim to make the user feel like they're physically manipulating the artifact, but when you're working with something with your hands, it pushes back against you. How do we recreate that in virtual reality? Take a moment real quick and reflect on some of the tasks you perform with computers day to day. What are some of the places where you don't interact through direct manipulation? If you're having trouble thinking of one, think especially about places where technology is replacing things you used to do manually. Chances are the physical interface was a bit closer to the task than the new technical one. How can the technical interface better leverage direct manipulation? So when I was writing the script for this exact video, I was interrupted by a text message from a friend of mine. And in the reply I was writing, I wanted to include a smiley face. We know that using emojis and emoticons tends to humanize textual communication. On my phone, the interface for inserting an emoji is to tap an icon to bring up a list of all the emojis and then select the one that you want. But when I'm reacting to someone in conversation, I'm not mentally scrolling through a list of all my possible emotions and then choosing the one that corresponds. I'm just reacting naturally. Why can't my phone capture that? Instead of having to select smiling from a list of emotions, maybe my phone could just have a button to insert the emotion corresponding to my current facial expression. So to wink, I would just wink. To frown, I would just frown. It wouldn't be possible to capture every possible face, but for some of the most commonly used ones, it might be more efficient. There may be no better example of the power of direct manipulation than watching a baby use an interface. Let's watch my daughter Lucy try and use her Kindle Fire tablet. My daughter Lucy is 18 months old, yet when I give her an interface that uses direct manipulation, she's able to use it. She wouldn't be able to use a keyboard or a mouse yet, but because she's directly interacting with the things on the screen, she can use it. Actually, there might be an even better example of direct manipulation in action. There are games made for tablet computers for cats. Yes, cats can use tablet computers when they use direct manipulation. Let's try a quick exercise on direct manipulation. The Mac touchpad is famous for facilitating a lot of different kinds of interactions. For example, I can press on it to click, press with 2 fingers to right click. I can pull up and down with 2 fingers to scroll up and down. I can double tap with 2 fingers to scroll in and out a little bit. And I can pinch to zoom in and out a lot more. Which of these are good examples of direct manipulation in action? Now there's some room for disagreement here, but I think these 5 seem to be pretty cut and dry. We can think about whether or not these are direct manipulation by considering whether or not what we're doing to the touchpad is what we'd like to do to the screen itself. For clicking, I would consider that direct manipulation because just as we press directly on the screen, we're pressing directly on the touchpad. Right-clicking though, the 2-finger tap, doesn't really exemplify direct manipulation because there's nothing natural about using 2 fingers to bring up a context menu as opposed to using 1 to click. We have to kind of learn that behavior. Scrolling makes sense because with scrolling, it's like I'm physically pulling the page up and down to see different portions of it. The 2-finger tap for zooming in and out a little bit though, isn't really direct manipulation because there's no real clear reason that needs to zoom in and zoom out. Pinching, on the other hand though, makes sense because it's as if I'm physically grabbing the page and shrinking and enlarging it. So some of these, I would say, are pretty good examples of direct manipulation, while others are things that we kind of have to learn to do. The Mac touchpad has some interesting examples of how you can make indirect manipulation feel more direct. For example, if I swipe from the right to the left on the touchpad with 2 fingers, it pulls up this notification center over on the right. This feels direct because the notification center popped up in the same place on the screen that I swiped on the touchpad. The touchpad is almost like a miniature version of the screen. But they could have placed the notification center anywhere and used any kind of interaction to pull it up. This isn't like scrolling where there's something fundamental about the content that demands a certain kind of interaction. They could have designed this however they wanted. But by placing the notification center there and using that interaction to pull it up, it feels more direct. Now, animation can also help us accomplish this. On the touchpad, I can clear the windows off my desktop by kind of spreading out my fingers on the touchpad. And the animation shows them going off to the side. And while that's kind of like clearing off your desk, I'd argue it's not close enough to feel direct, except that the animation on screen mimics that action as well. The windows could have faded away, or they could have just slid to the bottom and still accomplished the same function of hiding what's on my desktop. But the animation they chose reinforces that interaction. It makes it feel more direct. The same thing actually applies with the Launchpad, which we bring up with the opposite function by pinching our fingers together. The animation looks kind of like we're pulling back a little bit or zooming out, and we see the Launchpad come into view, just as the gesture is similar to zooming out on the screen. So direct manipulation isn't just about designing interactions that feel like you're directly manipulating the interface. It's also about designing interfaces that lend themselves to interactions that feel more direct. Depending on the area of HCI that you chose to explore, direct manipulation might be a big open question. So for gesture-based interaction, for example, you're generally not actually touching anything. Direct manipulation is contingent on immediate feedback that maps directly to the interaction. So how do you create that in a gesture-based interface? This is a big challenge for virtual reality as well. Virtual reality thrives on making you feel like you're somewhere else, both visually and auditorily, but it has a long way to go kinesthetically. How do you create the feeling of direct manipulation based on physical action when you can only give feedback visually or auditorily? So take a second and reflect on how these principles of direct manipulation apply to your chosen area of HCI. Whether through using direct manipulation, through innovative approaches to shrinking these gulfs, or through the user's patience and learning, our ultimate goal is for the interface between the user and the task to become invisible. What this means is that even though there is an interface in the middle, the user spends no time thinking about it. Instead, they feel like they're interacting directly with the task rather than with some interface. So for example, I have a stylus, and I'm going to write on this tablet computer. I'm interacting with an interface, which is translating my drawing into data in the system. But for me, this feels just like I'm writing on a normal page. That feels just like writing on paper. This interface between me and the data representation of my drawing underneath is pretty much invisible. I feel like I'm writing on paper. Contrast that with trying to draw with a mouse. That feels extremely unnatural. I'm very well aware of the mouse as an interface between myself and this drawing task. So the direct manipulation facilitated by the stylus gets me much closer to my task and helps the interface disappear between me and what I'm trying to accomplish. Good design. Interfaces that are metaphorically invisible. Bad design. Interfaces that are literally invisible. Well, kind of. Gesture-based interfaces are, in one sense, literally invisible. That's actually why it's so important to give great feedback, because otherwise it's tough to gauge the success of a gesture interaction. We shouldn't fall into the trap of assuming that just because an interface has become invisible, the design is great. Interfaces become invisible not just through great design, but also because users learn to use them. With enough practice and experience, many users will become sufficiently comfortable with many interfaces to feel invisibly integrated into the task. So, take driving for example. Let's say I'm driving a car and I discover I'm headed right for someone. What's my reaction? Well, I turn the wheel to the side and I press my brake. It's instinctive. I do it immediately. But think about that action. If I was just running down the street and suddenly I saw someone in front of me, would it be natural for me to go like that? Of course not. The steering wheel was an interface I used to turn to the left, but it's become invisible during the task of driving because of all my practice with it. But just because the interface has become invisible doesn't mean it's a great interface. People spend months learning to drive, they pay hundreds of dollars for classes, and they have to pass a complicated test. Driving is important enough that it can have that kind of learning curve. But for the interfaces that we design, we generally can't expect users to give us an entire year just to learn to use them. We'll be lucky if they give us an entire minute to learn to use them. So our goal is to make our interfaces invisible by design. Our goal is to create interfaces that are invisible from the moment the user starts using them. They should feel immediately as if they're interacting with the task underlying the interface. Now this is an extremely tall order and one we honestly probably won't meet very often, but it's the goal. In fact, in my opinion, this is why people tend to underestimate the complexity of HCI. When you do things right, people won't be aware that you've done anything at all. So how do we create interfaces that are invisible from the very first moment the user starts using them? That's precisely what we'll discuss in a lot of our conversations about HCI. We'll talk about principles for creating interfaces that disappear, like leveraging prior expectations and providing quick feedback. We'll also talk a lot about how to get inside the user's head and understand what they're seeing when they look at an interface so that we can make sure that their internal mental model matches the system. In fact, if we consider invisibility to be a hallmark of usable design, then this entire course could be retitled Creating Invisible Interfaces. Here are 5 tips for designing invisible interfaces. Number 1, use affordances. We talk more about affordances when we discuss design principles and heuristics, but affordances are places where the visual design of the interface suggests how it's supposed to be used. Buttons are for pressing, dials are for turning, switches are for flicking. Use these expectations to make your interface more usable. Number 2, know your user. Invisibility means different things to different people. Invisibility to a novice means the interactions are all natural, but invisibility to an expert means maximizing efficiency. Know for whom you're trying to design. Number 3, differentiate your user. Maybe you're designing something for both novices and experts. If that's the case, provide multiple ways of accomplishing tasks. For example, having copy and paste under the Edit menu keeps those options discoverable, but providing Control-C and Control-V as shortcuts keep those actions efficient. Number 4, let your interface teach. When we think of teaching users how to use our software, we usually think of tutorials or manuals, but ideally the interface itself will do the teaching. For example, when users select copy and paste from the Edit menu, they see the hotkey that corresponds to that function. The goal is to teach them a more efficient way of performing the actions without requiring them to already know that in order to do their work. Number 5, talk to your user. We'll say this over and over again, but the best thing you can do is talk to the user. Ask them what they're thinking while they use an interface. Note especially whether they talk about the task or the interface. If they're talking about the interface, then it's pretty visible. Reflecting on where we've encountered invisible interfaces is difficult because they were invisible. What makes them so good is the fact that we didn't have to notice them. But give it a try anyway. Try to think of a time when you picked up a new interface for the very first time and immediately knew exactly how to use it to accomplish the task you had in mind. One of my favorite examples of an interface that is invisible by design comes from a video game called Portal 2. In lots of video games, you use a control stick to control the camera in-game, but different people have different preferences for how the camera should behave. Some feel if you press up, you should look up. Others, like myself, feel if you press down, you should look up, more like you're controlling an airplane with a joystick. In most games, you have to set this manually by going to Options, selecting camera controls, and enabling or disabling a Y-axis, and it's just a chore. But in Portal 2, watch what happens.
You will hear a buzzer. When you hear the buzzer, look up at the ceiling. Good. You will hear a buzzer. When you hear the buzzer, look down at the floor. Good. This completes the gymnastic portion of your mandatory physical and mental wellness exercise.
Did you see that? It was so subtle you might not have even noticed it. A character in the game asked me to look up. The game assumed whichever direction I pressed was the way I would want to press when I want to look up, and it set my preference accordingly. No option screen, no changing settings, the game automatically and invisibly had me complete my goal of correctly setting my camera preference. For this design challenge, let's tackle one of the most common problems addressed in undergraduate HCI classes, designing a better remote control. Now these probably aren't very good interfaces, and that's not to say that they're poorly designed, but the constraints on how many different things they have to do and how limiting the physical structure can be make these difficult to use. You might have seen humorous images online of people putting tape over certain buttons on the controls to make them easier to use for their parents or their kids. How do we design an invisible interface for a universal remote control, one that doesn't have the learning curve that these have? Personally, I think this is a great candidate for a voice interface, and in fact, Comcast, Amazon, and others have already started experimenting with voice interfaces for remote controls. One of the challenges with voice interfaces is that generally the commands aren't very discoverable. Generally, if you don't know what you can say, you have no way of finding out. But watching TV and movies is such a normal part of our conversations that we already have a vocabulary of how to say what we want to do. The challenge is for us designers to make a system that can understand that vocabulary. That way, when I say watch Community, it understands that Community is a TV show, and it tries to figure out, do I grab it from the DVR? Do I grab it from on demand? Do I see if it's on live? The vocabulary for the user was very natural. So for example, watch Conan.
Well, tonight a fan named David Joyner thinks he caught a mistake. He says it happened when I was telling a joke recently about Rand Paul.
Hey Conan, I was watching your episode on April 17th, and you said that Rand Paul wanted to run for president. I had to put that in there somewhere. Today we've talked about two applications of effective feedback cycles, direct manipulation and invisible interfaces. We talked about how interfaces are most effective when the user has a sense that they're directly manipulating the object in their task. We talked about how modern technology, like touchscreens and virtual reality, are making it possible for manipulation to feel more and more direct. We talked about how the most effective interfaces become invisible between the user and their task, such that the user spends no time at all thinking about the interface. And we talked about how interfaces can become invisible via either learning or design, and we're most interested in designing them to become invisible. To a large extent, that's the definition of usable design, designing interfaces that disappear between the user and their task. Human-computer interaction starts with human, so it's important that we understand who the human is and what they're capable of doing. So in this lesson, we're going to bring up some psychology of what humans can do. We'll look at three systems: input, processing, and output. Input is how stimuli are sensed from the world and perceived inside the mind. Processing is cognition, how the brain stores and reasons over the input it's received. Output is how the brain then controls the individual's actions out in the world. Now we're going to cover a lot of material at a very high level. If you're interested in hearing more, I'd recommend taking a psychology class, especially one focusing on sensation and perception. We'll put some recommended courses in the notes. In discussing human abilities, we're going to adopt something similar to the processor view of the human. For now, we're interested in what they can do, physically, cognitively, and so on. So we're going to focus exclusively on what's going on over here. We're going to look at how the person makes sense of input and how they then act in the world. And right now, we're not going to worry too much about where that input came from or what their actions in the world actually do. Notice that in this lesson, we're discussing the human almost the same way we discuss the computer or the interface in most lessons. The human is something that produces output and consumes input, just like a computer might be otherwise. But for now, we're only interested in how the human does this. Let's start by talking a bit about what the average person can sense and perceive. So here we have Morgan again. Morgan has eyes. Morgan's eyes are useful for a lot of things. The center of Morgan's eye is most useful for focusing closely on color or tracking movement. So we can assume that the most important details should be placed in the center of her view. Morgan's peripheral vision is good for detecting motion, but it isn't as good for detecting color or detail. So while we might use her periphery for some alerts, we shouldn't require her to focus closely on anything out there. As a woman, Morgan is unlikely to be colorblind. She has about a 1 in 200 chance. Men have a much greater prevalence of colorblindness at about 1 in 12. Either way, that's a significant body of people, so we want to avoid relying on color to understand an interface. We can use it to emphasize knowledge that it's already present in the system, but using the system shouldn't rely on perceiving color. Sight is directional. If Morgan's looking the wrong way or has her eyes closed, she'll miss visual feedback. As Morgan gets older, her visual acuity will decrease. So if we're designing something with older audiences in mind, we want to be careful of things like font size. Ideally, these would be adjustable to meet the needs of multiple audiences. Altogether, though, Morgan's visual system is hugely important to her cognition. The majority of concepts we cover in HCI are likely connected to visual perception. Morgan also has ears. Morgan can discern noises based on both their pitch and their loudness. Her ears are remarkably good at localizing sound as well. In fact, she can tell the difference between a nearby quiet sound and a faraway loud sound, even if their relative pitches and loudnesses are the same when they reach her ear. Unlike vision, hearing isn't directional. Morgan can't close her ears or point her ears the wrong direction, so she can't as easily filter out auditory information. That might be useful for designing alerts, but it's problematic for overwhelming her or sharing too much information with the people around her. Morgan's skin can feel things. It can't feel at a distance, but it can feel when things are touching right up against it. It can feel a variety of different types of input, like pressure, vibration, and temperature. Like listening, Morgan can't easily filter out touch feedback, but unlike listening, touch feedback is generally only available to the person it's touching, so it can be used to create more personal feedback. Traditionally, touch feedback or haptic feedback has been very natural. Morgan feels the keys go down as she presses them on a keyboard. But with touchscreens, motion controls, and virtual reality, touch needs to be more and more designed explicitly into the system if we're to use it. Let's design something for Morgan real quick. Let's tackle the common problem of being alerted when you've received a text message. Here are the constraints on our design for Morgan. It must alert her whether the phone is in her pocket or on the table. It cannot disturb the people around her. And yes, vibrating loudly against the table counts as disturbing the people around her. You're not restricted to just one modality though, but you are restricted to the sensors that the phone has available. So here's one possible design. We know that smartphones have cameras and light sensors on them. We can use that to determine where the phone is and what kind of alert should trigger. If the sensor detects light, that means the screen is visible, so it might alert her simply by flashing its flashlight or illuminating the screen. If the sensor does not detect light, it would infer that the phone is in her pocket, and thus would vibrate instead. Now, of course, this isn't perfect. It could be in her purse, or she could have put it face down. That's why we iterate on a design like this to improve it based on the user's experiences. After the perception portion of this model comes the cognition portion, starting with memory. There are lots of different models of memory out there. For our purposes, we're going to talk about 3 different kinds of memory: the perceptual store or working memory, the short-term memory, and the long-term memory. Some scientists argue that there are other types of memory as well, like an intermediate sort of back-of-the-mind memory, but the greatest consensus is around the existence of at least these 3 kinds. So let's start with the first, the perceptual store or the working memory. The perceptual store is a very short-term memory lasting less than a second. One of the most common models of working memory came from Baddeley and Hitch in 1974. They described it as having 3 parts. First, there's the visuospatial sketchpad, which holds visual information for active manipulation. So for example, picture a pencil. The visuospatial sketchpad is where you're currently seeing that pencil. A second part is the phonological loop. The phonological loop is similar, but for verbal or auditory information. It stores the sounds or speech you've heard recently, such as the sound of me talking to you right now. A third part is the episodic buffer. The episodic buffer takes care of integrating information from the other systems, as well as chronological ordering to put things in place. Finally, all 3 of these are coordinated by a central executive. So let's try an example of this. I'm going to very quickly show you a picture, then ask you a question about it. Don't focus on any particular portion of the picture. Try to view it as a whole. What was the score on the scoreboard? As you can now see, the score was 0 to 0. Now, as you tried to reason over that, what you probably did was picture the image in your mind. That was trying to reason over what was stored in the perceptual buffer, and it decayed very quickly. However, if you're a fan of baseball, you probably had a better chance of getting that right. That's because you have some domain expertise. You're better able to process images about that domain more quickly. You might, for example, have recognized that most of the innings weren't marked. So that increases the odds that the score of the game was pretty low. This idea is actually the foundation of a fascinating study about chess experts versus novices and recognizing the configuration of chessboards. The study found that experts were far better than novices at remembering realistic chessboards that were only flashed for a short period of time, like the one on the left. But experts were no better than novices at remembering random chessboards. So expertise or rehearsal delays the decay of the perceptual buffer. When we're designing interfaces, short-term memory is one of our biggest concerns. It's important we avoid requiring the user to keep too much stored in short-term memory at a time. Current research shows that users can really only store 4 to 5 chunks of information at a time. For a long time, there was a popular idea that people could store 7 plus or minus 2 items in memory at a time, but more recent research suggests that the number is really 4 to 5 chunks. There are 2 principles we need to keep in mind here, though. The first is the idea of chunking. Chunking is grouping together several bits of information into one chunk to remember. So to illustrate this, let's try it out. I'm about to show you 6 combinations of letters. Try to memorize them, and then enter them into the exercise that pops up. Are you ready? Now, to keep you from just rehearsing it in your perceptual store until you can re-enter it, I'm going to stall and show you some pictures of my cats. There's one, there's both of them, then here's my daughter. Okay, now fill in the words. So what happened? Well, what likely happened is that you maybe had only a little bit of trouble remembering the 2 real words that were listed on the right. You might have had some more trouble remembering the 2 words that were listed in the middle that were fake words but that nonetheless looked like real words. And you probably had a lot of trouble remembering the 2 series of letters over on the left. Why is all that? Well, when it came to memorizing these 2 words, you were just calling up a chunk that you already had. You didn't see these as arbitrary collections of letters, you saw them as words. For the ones in the middle, you've never seen those combinations of letters before, but you could pronounce them as if they were words, so you likely saw them as fake words rather than just random collections of letters. For these over on the left, though, you had to memorize 5 individual characters, so that means that while these 4 were able to be chunked into words or pseudo-words, these likely had to be remembered as 5 chunks each. That makes this much more difficult to remember than these. However, there is a way we can make this easier, so let's ask a different question. Which of these 6 words did you see in the exercise previously? Even if you had trouble just naming these series of letters in the exercise previously, you probably were much more successful at this exercise. Why is that? That's because it's far easier to recognize something you know than to recall it independently. That's a useful takeaway for us as we design interfaces. We can minimize the memory load on the user by relying more on their ability to recognize things than to recall them. So what are the implications of short-term memory for HCI? We don't want to ask the user to hold too much in memory at a time. 4 to 5 chunks is all. Asking the user to hold 10 numbers in short-term memory, for example, would probably be too much. But we can increase the user's effective short-term memory capacity by helping them chunk things. For example, this is probably by far easier to remember even though it's the same content. We've chunked 10 items into 3, and we've used a format for phone numbers with which you're probably familiar if you're in the United States. If you're from outside the US, you might be familiar with a different grouping, but the same principle applies. And finally, when possible, we should leverage recognition over recall. For example, if I ask you to recite the number, maybe you could. In fact, go ahead, try it. Whether or not you could do that, you almost certainly, though, can pick it from this list. This is one of the reasons why menu bars and tool strips are so ubiquitous in software design. The user doesn't have to remember the icon for a command or the name of an option. They just have to recognize it when they see it. Finally, we have long-term memory. Long-term memory is a seemingly unlimited store of memories, but it's harder to put something into long-term memory than to put it into short-term memory. In fact, to load something into long-term memory, you generally need to put it into short-term memory several times. To demonstrate this, I'm going to describe something called the Lightner system. The Lightner system is a way of memorizing key value pairs, or in other words, memorizing flashcards. Those could be words and their definitions, countries and their capitals, laws and their formulas, anything where you're given a key and asked to return a value. So I have some flashcards here that have the capitals of the world. What I do is go through each one, read the country, check to see if I remember the capital, and if I do, I'll put it in the pile on the right. If I read the country and don't know the capital, I'll put it in the pile on the left. So let me do that real quick. Now tomorrow, I would just go through the pile on the left. Any that I remember from the pile on the left tomorrow, I'll move to the pile on the right. Any that I still don't remember will stay in the pile on the left. So I'm focusing my attention on those that I don't yet know. In 4 days, I'll go through the pile on the right. And any that I don't remember then, I'll move back to my pile on the left to remind me to go through them each day. So the things that I remember least are most often loaded into short-term memory, solidifying them in my long-term memory. Now in practice, you wouldn't do this with just 2 piles, you'd do it with 3 or 4 or 5, and the longest duration pile you might only go through yearly just to see if it's decayed yet. To talk about cognitive load, let's think for a moment of the brain like it's a computer. The community is actually divided on whether or not the brain actually operates this way, but for the purposes of this explanation, it's a useful metaphor. So your brain has a certain number of resources available to it, the same way your computer has a certain number of processor resources available to it. Each thing that the brain is working on takes up some of those resources. Let's say you're at home in a quiet area working on a calculus problem that requires 60% of your cognitive resources. In that setting, you have plenty of resources to solve that problem. However, then you go to take a calculus test. Now you have some stress in there. Now you're stressing about the impact this test is going to have on your grade. You're stressing about how well other people seem to think they're doing on it, whether or not other people seem to be struggling while you struggle. This is taking up a lot of your cognitive resources. Here we see the stress taking up 50% of the cognitive resources you have. Now you don't have sufficient resources to complete the problem successfully. I hypothesize that's why test-taking anxiety can have such a negative effect. It takes resources away from actually working on the test. You can apply these same principles to the presence of distractions, anxiety disorders, and more. Cognitive load has 2 major applications to our work in designing interfaces. One, we want to reduce the cognitive load posed by the interface so that the user can focus on the task. Second, we want to understand the context of what else is going on while users are using our interface. We need to understand what else is competing for the cognitive resources users need to use our interface. If we're designing a GPS or a navigation system, for example, we want to be aware that the user will have relatively few cognitive resources because they're focusing on so many things at once. Let's take a second and reflect on cognitive load. Try to think of a task where you've encountered a high cognitive load. What different things did you have to keep in mind at the same time? And how could an interface have actually helped you with this problem? Computer programming is one task with an incredibly high cognitive load. At any given time, you're likely holding in working memory your goals for this line of code, your goals for this function, your goals for this portion of the program as a whole, the variables you've created, and a lot more. That's why there's so many jokes about how bad it is to interrupt a programmer, because they have so much in working memory that they lose when they transition to another task. But there are ways good IDEs can help mitigate those issues. For example, inline automated error checking is one way to reduce the cognitive load on programmers because it lets them focus more on what they're trying to accomplish rather than the low-level syntax mistakes. In that way, the IDE offloads some of the responsibility from the user to the interface. Now we could phrase that a little bit differently too. We could describe this as distributing the cognitive load more evenly between the different components of the system, myself and the computer. That's a perspective we discuss when we talk about distributed cognition. Here are 5 quick tips for reducing cognitive load in your interfaces. Number 1, use multiple modalities. Most often that's going to be both visual and verbal, but when only one system is engaged, it's natural for it to become overloaded while the other one becomes bored. So describe things verbally and also present them visually. Number 2, let the modalities complement each other. Some people will take that first tip and use it as justification to present different content in the 2 modalities. That actually increases cognitive load because the user has to try to process 2 things at once, as you just noticed when Amanda put something irrelevant up while I said that. Instead, focus on letting each modality support, illustrate, or explain the other instead of competing with the other. Number 3, give the user control of the pace. That's more pertinent in educational applications of cognitive load, but oftentimes interfaces have built-in timers on things like menus disappearing or selections needing to be made. That dictates the pace, induces stress, and raises cognitive load. Instead, let the user control the pace. Number 4, emphasize essential content and minimize clutter. The principle of discoverability says we want the user to be able to find the functions available to them, but that could also raise cognitive load if we just give users a list of 500 different options. To alleviate that, we can design our interfaces in a way that emphasizes the most common actions while still giving access to the full range of possible options. Number 5, offload tasks. Look closely at what the user has to do or remember at every stage of the interface's operation and ask if you can offload part of that task onto the interface. For example, if a user needs to remember something that they entered on a previous screen, show them what they entered. If there's a task they need to do manually, see if you can trigger it automatically. So our user has received some input, it's entered her memory, she's cognitively processed it, now it's time to act in the world in response. In designing interfaces, we're also interested in what is physically possible for users to do. This includes things like how fast they can move or how precisely they can click or tap on something. For example, here are 2 versions of the Spotify control widget that appears on Android phones. On the left is the version that's available in the tray of the phone that you can access at any given time by swiping down on the phone screen. And on the right is the version that appears on the lock screen when you turn on a locked phone while it's playing music. In each case, the X closes the app, which is consistent with a lot of other applications. The forward, back, and pause buttons are similarly consistent with their usual meanings. I don't actually know what the plus sign here does. It doesn't have a clear mapping to some underlying function. Now note on the left, we have the close button in the top right corner. It's far away from anything else in the widget. On the right, the close button is right beside the skip button. I can speak from considerable personal experience and say that the level of specificity or the level of precision required to tap that X instead of tapping the skip button is pretty significant. Especially if you're using this while running or driving or anything besides just sitting there interacting directly with your phone. The precision of the user's ability to tap on a button is significantly reduced in those situations. And in this case, that can lead to the quick error of closing the application when all you're trying to do is skip forward to the next song. This isn't an error in the perception of the screen. It's not an error in their memory of the controls. They're not thinking that the X button actually is the skip button. This is just an error in what they're physically able to perform at a given time. The interface relies on more precision than they would have in many circumstances. So this design doesn't take into consideration the motor system of the user or the full context surrounding usage of this application. This isn't as significant in the design on the left because there's more room around that close button. If I aim for the forward button and miss, the worst that's going to happen is I might pause it. I'm not going to close it by accident. This is one example of how we need to be aware of the constraints on the user's motor system, what they can physically do, how precise or accurate they can be, and so on. And we have to be aware of that in the context where the application is going to be used as well. These buttons are no smaller than the keys on a smartphone keyboard, but we expect more specificity when they're sitting there typing with their thumbs, as opposed to reaching over and interacting real quick on something on the lock screen. Now, of course, there might be other constraints around this. There might be a reason why this button is placed there. There might be some constraint in the Android system that doesn't let them use more than one row of the lock screen. In that case, we would need to make our interface more tolerant of errors. Maybe we require a double tap to close the app, or maybe we mute it when it's pressed and then give the user 5 seconds to confirm that that's actually what they want to do. Those are ways of reducing the penalty for errors. We've talked a lot about different human abilities in this lesson. Depending on the domain you chose, the human abilities in which you're interested may vary dramatically. If you're looking at gestural interfaces or wearable devices, then the limitations of the human motor system might be very important. On the other hand, if you're interested in educational technology, you're likely more interested in some of the cognitive issues surrounding designing technology. For virtual reality, your main concern will likely be perception, although there are interesting open questions about how we physically interact with virtual reality as well. So take a few moments and reflect on what the limitations of human ability are in the domain of HCI that you chose to explore. Today we've gone through a crash course on human abilities and perception. We started off by talking about the main ways people perceive the world around them through sight, sound, and touch. Then we discussed some of the components of cognition, especially memory and learning. Then we discussed the motor system, how the person then interacts with the world around them. In this single lesson, we've only scratched the surface of human perception. There are entire courses, even entire degree programs that focus on these principles. We'll give you some suggestions on some in the notes. So don't think we've given you a full view of the field. Instead, we hope we've given you just enough to start to keep human abilities in mind, and enough to know what to research as you start to learn to design interfaces.